unicorns.
This show is all about the people behind the science of biotechnology and medical devices. Through the stories of the people, I hope that Lab Rats to Unicorns is able to describe the transformative process of, how an idea starts in the lab and eventually becomes a life-saving treatment or a product that helps patients with diseases.
Life-saving.
All right, everybody. Today's guest is Dr. Kate Rubins, a microbiologist and NASA astronaut who made history as the first person to sequence DNA in space. She holds a BS in molecular biology from UC San Diego and a PhD in cancer biology from Stanford. Before joining NASA, she led a research team at the Whitehead Institute studying viral diseases such as Ebola and Lassa fever, and worked with the CDC and U.S. Army to develop models for smallpox infection. As an astronaut, Dr. Rubins has spent 300 days in space across 2 missions, served as a flight engineer on Expedition 63-64, and completed 4 spacewalks. Her groundbreaking work in space includes DNA sequencing and studying the effects of microgravity on biological systems. She also serves as a major in the U.S. Army Reserve, contributing to health services innovation. Dr. Rubins, welcome to the podcast.
Thank you. It's great to be here.
Well, I'll just kind of dive right in, and it's always good to kind of start from where you are today and maybe work backwards and just hear a little bit about what got you engaged, first in microbiology, and then what were some of the twists and turns that led you to getting engaged through NASA and ultimately into space.
Yeah, so I'm currently a NASA astronaut. I've been with NASA since 2009. And I've flown twice to the International Space Station, done a lot of science experiments up there. It was a total of 300 days across both of my missions. But I did not start out thinking that I was going to be an astronaut. Maybe when I was 5, right?
Yeah,
I wanted to be an astronaut, a biologist, and a geologist, all 3, because I thought you could have 3 careers. Yeah. So that's what I was aiming for.
Yeah.
And then I got really fascinated by biology. So I actually participated in high school in a HIV outreach program that had us educating our peers on HIV and how to prevent HIV transmission. And so I learned about the virus, as a high school student. I thought, gosh, this is amazing. It was kind of a terrible virus at this point, but there's all these scientists that are working on this virus, and they're trying to save people's lives. And so I knew that I wanted to go into research, and I wanted to go into scientific research because I could see this immediate impact, even as a high school student. So when I went to UC San Diego, I worked in the infectious disease laboratory with Rick Bushman, and so I worked on HIV-1 and HIV integration. And right away, getting pulled into the research, we were starting to look for antiviral compounds. So at that point, there were no integrase inhibitors developed, and HIV was still pretty much a death sentence. It was evolving resistance. And so the pressure was on to do screens and to find compounds that could inhibit HIV. And that just really got me into the world of research and excited about what we could do for human health. When I went to grad school, I shifted over to things like smallpox and Ebola and Marburg. And I worked a lot with the Army to develop therapies for these kinds of diseases, and then also just to study them, better understand how these viruses affect the human body and what we could do to fight them off or to prevent illness from these viruses. Then I started my own research lab at the Whitehead Institute at MIT, and continued all of the work that I was doing. Kind of the neat thing about that chapter was that I actually started a lab in the Democratic Republic of Congo as well.
Oh, wow.
That was really where we could get primary sources of these viruses.
Like field, okay.
Yeah,
sure.
Yeah. So, most people run from an Ebola outbreak. We were usually headed right towards it.
Yeah.
So we studied a lot of Mpox there as well. And, that was really interesting, learning how to do research in a developing country, how different that was from doing standard bench research where you've got sort of unlimited supplies and power and water. You don't think about these things very much. And it actually ended up being really helpful to be in that mindset when I was in space doing research as well.
Yeah.
So
very interesting. Yeah. And you're talking about a very important time, with regards to, HIV and AIDS. Really an epidemic, and you were really at the heart and the center of a lot of the discoveries that were being made at that time, especially on the biology end. One of our guests earlier had the chance to talk to Dr. Dennis Leota. He makes compounds, that would be screened in probably your biological screens, and along the way was a big, a part of helping, to develop drugs that ultimately, Big Pharma was able to take to patients. But I think it's so easy today to forget how serious and really just how the massive negative impact that it had on human health.
Yeah.
And to see discoveries that you've contributed to kind of make that impact to today, not really to worry not so much about it.
Yeah.
Although it's still obviously a very serious situation and a deadly disease, but the importance of those discoveries have helped us kind of keep it in check. Well, so maybe then transition. You're in the Republic of Congo. You're obviously continuing to develop expertise in microbiology, understanding some of these very nefarious viruses. What got you then engaged in moving down the pathway to become an astronaut?
Yeah, it's actually a little bit of a funny story.
Okay, well, let's hear it.
When I was a kid, I wanted to be I was a kid. I wanted to be an astronaut, but you put that away when you're not 5 anymore.
Yeah, I did too. Yeah.
This isn't a career. You can't major in astronaut. So I was on the scientist path. I was running a research lab, and I was working on a grant with my coworker. And the grant wasn't going particularly well. And we were a little frustrated, and we'd been at it. You get punchy, right, when you spend too much time working on a document. So she started looking for other jobs online because she's like, I don't know if we're going to get this grant. We may need to find new careers. It was a distraction. We were basically procrastinating instead of writing the grant. Yeah. And she called me and she says, Kate, there's applications to be astronauts online at usajobs.gov.
Oh my gosh.
Didn't you want to be an astronaut when you were a kid? And I was like, yeah, but that's not a thing that people do.
Yeah.
And she's like, we should apply to be astronauts. So, we hang up. I applied to be an astronaut. I really didn't want to write this grant. And I called her the next day and I said, Lisa, I got my astronaut application in. How's yours? And she's like, you don't always know when I'm joking. She was kidding.
That's great. Yeah.
And I said, well, don't worry. NASA's never going to hire a biologist. And so I was incredibly surprised when they called.
Yeah.
And started down that road for that interview process.
That's crazy. And did you make the grant application, or did that just kind of go by the wayside?
We did get the grant in.
I was in suspense.
After a little diversion, yeah.
No, that's really cool. And what was driving NASA to kind of move in this direction? I would imagine, just maybe trying to understand human health in space, but tell us a little bit more about what their motivation was to, put out that call.
Yeah, absolutely. So definitely they're interested in understanding human health. There's so many amazing things that happen to the human body when you go into space, good and bad. You're really rapidly changing. You get out of homeostasis and you're really adapting to this completely new environment. And so from the biological side, that's very interesting to study from the molecular level and the cellular level. But there also started to be a realization that, we've built this amazing International Space Station. We have a huge research capability. And one of the really interesting things to study up there is biological systems and what happens to these systems under microgravity. So I can give you a few examples of strange things that happen in space, like stem cells proliferate much faster. There's some kinds of cancer cells that become much more aggressive, which can then help you lead to a lot quicker screening if these cancer cells are much more aggressive.
Okay.
You've got all kinds of interesting physiologic changes for the humans, for fluid shifts. We've been doing a lot of work with organoids up there to see how they behave in microgravity. And so the list goes on, right? There's a huge amount of biological research. And when I came to NASA, they were just really getting going with a lot of these experiments and really outfitting the space station to do all of this molecular and cellular biology research. And so they didn't really hire me for that, but they were looking to add to the number of biological researchers, I think, in the astronaut corps.
Okay, understood. And as you dig a little bit deeper into the things that you did study in space, and maybe you could comment on a few of those experiments and maybe their applications. One would be application of health for astronauts that are in space for longer periods of time. But another, I would imagine too, is by understanding or getting insights through those experiments, maybe application here on Earth as well. But any comments on that?
Yeah, absolutely. So if you look at all the different physiological changes that happens for humans in space, a lot of those actually mimic diseases on Earth or various pathologies of aging. So for example, when we go to space, we lose a lot of bone. We lose it very quickly. We start to look very rapidly like a woman with osteoporosis who's 80 years old. We lose that much bone that she would lose in a year. We lose that much bone in a month without intervention. We've got a lot of muscle wasting. We have neurovestibular disorders, so balance disorders, vertigo, motion disorders. We have changes in our immune system where the immune system is kind of suppressed. We have really interesting changes in the fluid shifts up to your head because gravity's not drawing it back down to your feet. So very interesting things in the vascular system, cardiovascular system overall, changes with intracranial pressure and cerebral sinus. Basically every system that you can think of. Yeah. When you don't have, we don't pay attention to gravity, right? It's invisible. We just assume it's always there. Yeah. So when you take that away and then you see what the effect is in humans. So we've got this really interesting way to study a rapid onset of all of these processes. And they're not a slow aging decline, right? These are rapid onsets of things that are happening in healthy 30-year-olds and 40-year-olds. And then when we bring people back to the earth, we can study the reverse of that. And so it's very interesting to study the humans themselves. And I actually participate as a subject in many, many different research experiments when I'm up there. So, I'm the researcher, but I'm also the lab rat as well. Right. Yeah, that's great.
I
try to volunteer for as much science as I can. I put myself on the line physically.
Play a coach. Yeah, that's great. That's great.
But we can also look at cell biology. We can look at tissue culture models. We can look at animal models. Anything that you would want to in a molecular biology lab.
Well, and so tell us a little bit about sequencing DNA in space and maybe even just can you describe the environment that you're working in? I mean, it probably is kind of cramped, but maybe just give us some insight as to what it was like to even begin to do that work in an environment that probably would be, really difficult to work within.
Yeah, absolutely. It's the hardest thing is that everything's floating. And again, we take gravity for granted. You walk into your lab bench, right, or your desk at work, and things are just nicely laying on the desk or the bench. Yeah. This doesn't happen in space. You try to put something down, it's just going to float up. It's going to walk away. Most of the time astronauts are looking around for things that have been lost at some point. And so you really have to Velcro and tape everything down to the lab bench. We also had to think of a few different ways that we could be creative about how we're going to do this experiment because it involves fluids. And in microgravity, a bubble will form in a fluid. And you don't have gravity, so the liquid never sinks to the bottom of the container and the bubble doesn't rise to the top. So once you get a bubble in that system, it's just going to stay there. And then, you go back the next day and it seems like it's brought all its bubble friends. There's just even more bubbles in this liquid. And so that can be, not great for a sequencing machine. So we had to really think about how we could do this in the context of microgravity. And we said, you know what, let's just try it. We were assuming we were going to fail. And sometimes that's the best way to do an experiment. We don't think this is going to work. We're going to try it, but where it fails is going to be the interesting thing. Then we can go back and we can refine our hypothesis and we're going to try it again. And so we paid attention to bubbles. We paid attention to a few other things. Luckily, the device that we used was small and it involved microfluidics. So it wasn't, it wasn't something where we had a lot of lasers that we needed to align or a really big, complicated piece of equipment. And so we started running the prepared libraries on the sequencer, and it worked for the first time. And my experiments don't always work the first time. My grad students would always make fun of me when I go into the lab as a professor, and they're like, oh, maybe you go back to the office and you write some more grants, right? But this actually worked. It was a really good time to have an experiment work in space.
Yeah. Well, and if you look at some of those activities leading up to that, what were the preparations that you had to do, kind of, if you rewind a little bit, before you went on that mission? What were some of the things you had to be thinking about, even to be prepared, just bringing the right reagents, the right instruments? And maybe one other question alongside of that, as you're thinking about that, is you mentioned earlier that your experience in the Republic of Congo had some maybe instructional value to operating, in restricted conditions. Is that what you meant? And how did you apply that knowledge, in your space mission?
Yeah, absolutely. I think when we work in the lab right now, we kind of take for granted that we've got a Fisher VWR catalog. If we run out of pipette tips, we're just going to order some more. They'll be there in a few days. For a mission in Congo or a mission on the space station, you have to think about every single thing you're going to use for that mission. You need to work through the procedures. You need to practice it several times. Make sure you're not missing anything. You have to pack pack it up and you think about shipping it and how it's going to get there. And so the consumables and the supply chain becomes really important in the experiment. And then you also need to think about the experiment. How much power is it going to draw? Does your machine just automatically assume you've got cloud computing access and that's built into the software and it won't work otherwise? Do you have clean water available? How are you going to get water to run your experiment? How are you going to get solutions and reagents? And then what does your cold chain look like? So once you're getting ready to ship something, you want to ship it up there frozen in a -80, or you're going to bring a product back, you want that to be frozen as well, or at least kept cold. These are complicated things that we just assume we've got like a freezer in the lab. We've got a -80, it's right down the hall.
Yeah.
And so working in the Congo really trained me to think about every aspect of that experiment and to identify and really value ways that we could make things small and modular, and a little bit independent of all the infrastructure that we're used to. So I love this concept of working in a low resource environment. And you would never think of space being a low resource environment, but it is. Our power comes from solar arrays. Like, people are fighting about watts up on space station because we have a really limited amount of power. We don't have access to cloud computing. We've got limited infrastructure to send data back and forth, and we can, but you have to think about your bits that you're sending back and forth. So all of these things are, it designs, the way you design your research will be profoundly influenced by that. The great part about that is once you start thinking about that and you design research that would be really good for the space station, this research that research package would have worked perfectly in the Congo as well. I'm with the DoD. This kind of thing would work really well if you've got a bunch of soldiers that are very far forward and they're cut off from supply lines, and you need to do medical diagnostics or you need to do sampling. And so I think there's an opportunity here when we look at how we design things for space to see what other environments on Earth, like, how could we take this research out of the lab? Once you have that capability, kind of like the small sequencer that we used on the space station, it's a commercial product. Once you have that, all of a sudden people are in the forests of Colombia sequencing for biodiversity. They're in Antarctica with a sequencer because they couldn't bring the big machines with them before. And so if you design that entire infrastructure around things being small and modular, it really opens up like what you can do, where you can go, and you're not tied to a lab or a hospital or a high resource setting. Yeah, that's amazing. And I want to come back to that. I want to just finish up our conversation focus around your time in the ISS. But I want to come back to that point because I think that has implications on the future of biotech and innovation and how you bring a drug to patients and things getting smaller, and that kind of gets into the realm of small biotech companies and what 10 years out looks like and what type of impact, smaller, less resourced environments could create. But before we go there, just continue on if you don't mind. What was managing your psychology? So I would imagine it's kind of like scary or lonely or, just there's a lot on your mind to begin with, and then to be able to focus on some really specific experiments. Can you just walk us through some of your mind management while you're up there? Yeah, it's definitely something that we have to think about as astronauts and prepare for. Kind of one of our biggest mitigations is that we're up there with a crew, right? So we've got this group of amazing people. It's the International Space Station, so it's an international crew. And you get together with your crew members about 2 years before flight, and you start training together. So by the time you get to orbit, like, you really know, you're basically family. I've got space brothers and sisters, right? That, for life here. Sure. And so everybody really works as a crew. So you may be doing an individual experiment, but you may be doing that with another crew member, or somebody will come along and say, "Hey, can I help you clean up? I see you're a little bit behind your timeline." And so there's a lot of that really where we're relying on each other. The other thing is that it's why we're there. We're there to do science and we're there to do research. There's other things that goes along with it. We have to maintain the space station. We have to do spacewalks, right? We have to get our cargo vehicles docked to the space station. But the heart of why we're there is to do research and to do science. So it's kind of the thing, you wake up in the morning and you look at your schedule and you get really excited if you have a cool experiment on your schedule. You get maybe a little less excited if the toilet's broken and it's your day to fix it. Which does happen a lot in space. I can imagine. But it's part of the dealing with the isolation and the boredom and the repetition is just the fact that you get to touch so many different science experiments. And these aren't our personal experiments necessarily. Like we can help advise, but these are principal investigators. These are scientists around the world that have been working on this research. And so I did over 200 different investigations when I was up there.
Yeah.
And it's incredibly
you're really
exciting.
Stewarding, on behalf of
you're their hands, and we can get the principal investigators on a video call so you can actually talk to them.
Wow.
Some of my favorite times up there were talking to some grad students who are looking at fluid dynamics and how plants' roots might uptake fluid and nutrients and microgravity in a different way. We had this whole setup and they could see what I was doing on the video, and we start doing things, and I noticed a couple things. I'm like, hey, this is an interesting discussion. They went off, they got all excited, they went off, they came back 5 minutes later and they're like, can you try this condition? Can you try this one? Yeah. And we were just in real time making discoveries with this group of grads. Can you imagine that as a grad student and you're talking to the International Space Station and finding new things that nobody had ever discovered before.
In real time, like you said, too. Yeah. That's crazy. How long were you up there for that mission?
So my first mission was about 120 days, and the second one was 180 days.
That's a long time.
About 300 total.
And then, can you tell us a little bit about other things that you were doing? You mentioned, maintaining and supporting the space station. What about walking, the spacewalks? Can you give us a little bit of color around what's involved in that? And then just the feelings that you had doing that.
So, spacewalks they're incredibly challenging. It's sort of at the limits of what human beings can do.
The movies, they just seem pretty straightforward.
Oh, yeah. In the movies, they're never wearing tethers. Now that I mention that, you all are going to notice this in every space movie. We would never do a spacewalk without a tether. That's a very bad idea. One hand slips and all of a sudden you're your own satellite and you're not coming back, right? So definitely, if you're ever on a spacewalk, this is my advice, is you should tether yourself. So it's, we train for that at NASA. We have a giant swimming pool with an entire mock-up of the International Space Station underwater. And so we spend hundreds of hours training in a spacesuit underwater on the kinds of equipment that we need to fix, or sometimes we're doing experiments outside, or we're taking scientific equipment outside. So we train all of that. When you get to space, it's still a completely new experience, because underwater, you move kind of slowly and the water drag holds you in place. On the space station, you don't have any weight, but your body in your spacesuit still has mass. So once it starts going, it wants to keep going. And these spacesuits are like 300 pounds, right? So that plus you in it, it really is going to just keep going. There's nothing to stop it. And so a lot of what we spend our time on is learning how to stabilize ourselves, like understanding all these different forces. As we're crawling around on the outside of the space station, what forces are we inputting? And how do you do things like set up a piece of scientific equipment or bolt a large structure onto the space station? So it is, I have to say, it's a little terrifying the first time we go. We go out the door, right? We take a little walk. We sort of, we make it sound nice and cute, right? But, you're putting your spacesuit on and you're in relative safety inside the module, and it's nice, and you got all this oxygen there, and it's a nice temperature. You open the hatch, go outside, all of a sudden it's either minus 200 Fahrenheit or plus 200 Fahrenheit, and it's going to flip back and forth every 90 minutes between those things. And you're looking out into the vacuum of space. And so you definitely kind of prepare for that psychologically by repetition and by your training. And again, we never do a spacewalk alone. You always have a buddy, and that's there for safety reasons, so that person can rescue you or you can rescue them. And then it's also for the tasks that we need to do to have two people. So you're always working as a team outside, but we take it very seriously. It's definitely something that we're taking a lot of risk every time we open the hatch and depressurize the airlock, because we've got to, at the end of the day, we've got to get those two astronauts back inside a tiny hatch, get the hatch closed, and get it repressurized before they can come back into the space station. So
what was it like taking off?
Oh, launching.
Yes.
Oh, it's interesting. People say, what do you like better, like launching or landing? And I actually liked landing a little bit better. Launching is just crazy. Like you're just, at the beginning, it actually seems very normal, because you're sitting in a capsule that looks exactly like the simulator. And, I would look around, I'd look at all the buttons, and I'd spent hundreds of hours in the simulator training. So I just felt it was another day. I was in the sim. My crewmates are next to me. We're getting ready, for the instructors to make our lives miserable for the next few hours. So it was very calm. But then when you get to launch and the vehicle starts moving, I had never experienced anything like that.
Right.
And it's at that point, it's a little too late to back out, right? The hatch is closed and you're on top of a rocket. There's only one place that you're going, and it's going to be up. So, a lot of vibrations. There's a lot of G-force. But it's really quick. I don't know that most people know this, but it takes about 9 minutes to get to space from the Earth, because you end up going, so you accelerate from 0 miles an hour to 17,500 miles an hour in 9 minutes. You can feel that. You can feel that acceleration.
That's crazy.
It's over quickly. And we spend a lot of time thinking about what could go wrong and what we're going to do about it. And so you're sort of ready every second for something to go wrong and what your response would be. We've got procedures that we're following along, all the parameters that we're checking in the vehicle. So it's an incredibly mentally busy, compressed time frame. And there's no enjoyment of a launch. You're just like, let's get through this thing so I can get to space.
Yeah.
Whereas landing, it takes 33 minutes to come in. You burn your deorbit burn and you come in through the Earth's atmosphere and you go through this plasma fireball. Like, we're in a ball of superheated
what is that like? I mean,
plasma
fireball.
It's you just hope the ablative heat shield's doing well.
Oh, my God.
But there's a lot more time to be involved in the process. There's a lot of things that we can do if something goes wrong on reentry. Take over manual steering. There's a lot that the crew is responsible for.
Yeah.
But it's just the time dilation's a little bit better for you to actually experience it. And so that's I kind of enjoyed that part. The problem is you go through this plasma fireball and the parachutes come out and everybody's happy, but you've got one step to go, and that's where your capsule slams into the Earth, right? So this it's like a train accident followed by a car accident.
Yeah.
You're going to hit the Earth in a big metal ball. There's no way around that, right?
It just
or
keeps rolling.
If you're in a SpaceX vehicle, you're going to hit the ocean, which is about the same.
Yeah.
And so everybody's kind of a little tense still on the way back down, because you know that this is coming. And then and once you actually hit the planet and the capsule stops rolling, just the look on everybody's face, you're just like, oh, we're home. We're in one piece. I can't believe we made it.
Yeah. And then, so as a follow up to that, what's your first thought? Is there a favorite restaurant you like to go to afterwards, or is it would you just kind of stare at space, or what do you do to kind of reground yourself then at that point?
When you first get out of the capsule and you can actually smell the air, space station it doesn't smell bad, but it doesn't smell like anything. We don't have any plants up there. We don't have animals. Right. We don't have weather. So you don't even feel rain or breeze on your face for 6 months. And so when you get out and we look at the sunshine, and we landed in the Kazakh steppe, so you could just kind of smell the earth and the scrub brush, and there was a breeze, and it's just it's overwhelming how many amazing things there are on our planet and nature, and you get to experience this. So it feels really good to get out of the stinky capsule and back on the planet and know that you're just I didn't appreciate oxygen until I went to space, and coming back and there's all the oxygen that you could ever want on this planet in this atmosphere. And it's just free. Yeah. And it's never going to, the oxygen tank is never going to have a problem and get cut off. You're never going to have low oxygen in your environment, which it could be a worry on the space station.
The things we take for granted.
Absolutely.
Yeah. Well, switching gears to kind of present day, there's a lot of, focus on space travel right now. There's more people are going to space. There's a movement, to try to eventually get people to Mars, and even over long periods of time. Can you talk a little bit about where you see the field unfolding in that regard, and back to human health, and maybe some of the ongoing work that will be needed to support humans, living for longer periods of time, on Mars or wherever they may land?
Yeah, I think it's an incredibly exciting time in space right now. You're seeing the convergence of a lot of different things. We have a program, the Moon to Mars program. We're going back to the moon and we're pushing on to Mars and developing the technologies to get us there. We're also continuing our research in low Earth orbit. We don't want to lose that. We've really found a number of systems where you can only make these discoveries in space. Potentially, there's some things that you can only manufacture them in space. And some of these things are really of commercial interest to the Earth. Things like Keytruda, which is a drug from Merck that was crystallized in a way in space that allowed it to be an oral formulation instead of an IV formulation.
Interesting. Okay.
You know, there's a lot of interesting physiology that we're studying with organoid systems right now. I mentioned the cancer therapeutic screening. But there's a lot of things that we may also try to manufacture in space. There's a group that's looking at manufacturing corneas. A lot of what you can manufacture in space will be more perfect than you can do it on Earth because you don't have buoyancy-driven convection and you don't have disruption in the systems. Everything is just absolutely gentle, like those bubbles, right? You put them in the fluid and they just stay suspended. Yeah. And so that's really interesting from a manufacturing standpoint. So there might be a resurgence in things like manufacturing or maybe even biomanufacturing in low Earth orbit. And so NASA's keeping all of that going and working on turning a lot more of that over to commercial industry so that we can really push on to the moon and Mars. Okay. The moon and Mars are complex. You know, these are challenging places to go. It's a lot harder of a problem. You know, it's an order of magnitude more difficult than even being in low Earth orbit. A lot of that is the distance, the propulsion required to get there. You know, how much fuel you need to get to Mars, how much fuel you need to even be able to enter a low lunar orbit and land on the moon. And then how do you keep people there for a long time? Right. So a lot of the things that we're doing is trying to understand what are the factors that keep humans healthy in space and where do we see, we don't really want to call it disease, right? All these perturbations and kicking you out of homeostasis, like all your fluid shifts, these aren't really a disease, and the bone loss isn't a disease because all your body's doing is really adapting to the microgravity environment. It's like use it or lose it, right? It doesn't need bones up there. It's going to get rid of them. So it's not a disease until you come back to Earth. Okay, and then you need those bones all of a sudden. Sure. So what we're studying is these rapid physiologic changes. And we need to figure out, how far do those extend if we're talking about a 2.5-year voyage to Mars? And we also need a lot of innovation, I think, in these small, portable biotechnology type things, particularly in the field of diagnostics, but also in medicine in general. You know, if you're talking about point of care, bedside type devices, when you're on the space station, if you have a medical issue, we always have a lifeboat, and we can undock and get the astronauts home within 24 hours. And so we've got some capability to take care of them up there, but any major medical issue, we're just coming back to the planet. Now, as you start to go to the moon, you do your translunar burn. At the worst case scenario, it could take you 5 days to get back. And so from a medical standpoint, the difference between less than 24 hours and 5 days really changes your thinking about what you can do and what you can take care of. Mars, once you burn for Mars, you're on a 2.5-year trip. You're not coming back. And so any medical issue is going to have to be solved in space. And so that's really a forcing function behind a lot of this. You know, we're going to have to take the hospital and the lab with us. Right. We need to start thinking about AI models that can help with, non-experts solve medical problems. So, we'll probably have a physician with a crew, but what if the physician gets hurt? We have an interesting 20-minute comm delay on the way to Mars. So that doesn't allow for real-time communication. I see. Yeah. And so we're going to have the ability to be in communication with an expert back on the ground, but real-time, if you have trauma and you're stopping the bleeding and you need to deal with it, that's going to be that crew and then possibly their AI model that's going to help them through that.
It's got to be localized.
Absolutely.
Yeah, no, that's a daunting challenge. And are there any, when you talk commercial, are there companies working on this? Are there any interesting, areas or particular areas of focus that you're seeing some of those technology companies begin to contribute in a way that would be meaningful to try to move the needle with regards to the future, in these long space missions?
Yeah, absolutely. So for the low Earth orbit, NASA's actually funded, I think it's about 5 different companies to build space stations in low Earth orbit. Okay. And so they're going to continue to fund that to really kick off this low Earth orbit economy and this space economy. And so as we do that and we move into these commercial space stations, it's not just the one company. company that has a station, right, they're going to have a whole bunch of different partners, and all these partners are going to be able to bring their technologies into low Earth orbit. We're going to start to see, I think, a lot more manufacturing in space. We're also going to start to see, everybody thinks it's just space tourists, and the commercial aspect of space, that's there.
Sure.
But that is such a small part of it.
Right.
What's really a much bigger market is things like other governments that have not flown something to space. The number of participants in the International Space Station is great, but it's still a small handful of countries. And so a government that could be able to fly their astronaut to a space station, and NASA's going to use these space stations as well. Like we're going to send our astronauts there. And so the hope is if you have more of this going on and the economy starts becoming more self-sustaining, you can involve a lot more of the world in this. You're going to increase the amount of access to space. So researchers on the ground that maybe can't get their experiment up to the ISS right now would have a lot more opportunities to fly it. I think on the other side, on the exploration side, we're seeing an absolute explosion of the technology needed. And this is why space is so cool. People say, like, why are you going to space? Why are you wasting all this money? And there's no money in space. Like you can't even bring a dollar bill to space. All the money is spent on Earth.
Right. That's a fair point.
But what it does is what we saw in Apollo is this miniaturization drives things like, instead of having a computer with vacuum tubes that takes a whole room, now we've got more powerful computers we could ever imagine in our pocket, in our cell phone. That was all kickstarted by Apollo. And so as we're thinking about the moon and Mars, we really need to think about solutions that are going to be something that you can put in the back of like a Volkswagen Beetle, right? That's sort of the interior volume of a spacecraft. That really changes how you design things. When we go to the moon, we don't have GPS on the moon. Not only do we not have GPS, we don't even have magnetic fields. So compasses don't work on the moon. So how are the astronauts going to navigate on the moon, potentially in the dark, trying to do their science? Right. We're looking at really interesting things with 4G on the moon and different ways to triangulate position, new satellite constellations potentially. We've got a lot of investment in technology to take us to the moon and to send small rovers to the moon. With space, everything's limited by weight. Like how much weight can you get off the planet? And there's this rocket equation, right, where you've got to spend so much fuel just getting your rocket and your fuel tank to orbit that what you can actually deliver is a very small payload. And so when you have that restraint and that constriction, you develop new technologies to make use of very lightweight, small, portable, modular technologies that, maybe you're starting to link these things together in a swarm. Maybe you're figuring out communication pathways so that they can operate autonomously and not have to depend on Earth and to have a controller on Earth. And so you can kind of see, this might touch industries that have nothing to do with space, but you're going to develop that technology for this lunar mission. And because commercial's involved, they can go spin this off and they can make companies out of it.
It's amazing how you got this very unique, very focused ecosystem of companies. And has that changed over time with NASA? Like, have you watched different iterations of how NASA has evolved its own model? It seems to me there's just so much cooperation and collaboration, whether it's across different countries or industry, private, and commercial versus just government funded. But what's your take on that? Is that true, or is it remaining kind of the same as it has been since you started?
Yeah, it's really changing. It's incredibly exciting. When I came into NASA, it was the International Space Station. We were working with our big international partners. And so this is the US, Russia, Europe, Japan, and Canada. But that was it, right? Those were the international partners. And we had a lot of really large government contractors that were building, these big pieces of hardware. And what we've seen is this huge shift where we're still maintaining these amazing international partnerships, but now we're adding all these smaller countries in. We have something at NASA called the Artemis Accords, which is a set of principles about how we're going to get to the moon. And it does things like talk about science transparency and openness and protection of intellectual property and operating in space. It's like rules of kindergarten, like be nice and don't take other people's stuff. But we've codified this. Yeah. And this is the gold standard for anybody that wants to go to the moon with NASA is going to adhere to these set of principles. And there's more than 100 countries that have signed on. So we're really growing internationally who's participating.
And that's, just the numbers and the diversity has got to lead to more creativity, more innovation, moving the needle even further.
And because these countries can sign on without needing to build an entire module of the space station, right? They can contribute a small part, or they can contribute a sensor that goes on the rover, where people can do things that they just didn't have the budget to do before. And And so we're just inviting a lot more people to the table. And I think that's really going to increase our innovation. And, people will specialize in what they know how to do, and they'll invent things for the scale that they can contribute. On the commercial side, again, we used to have like a lot of these really big aerospace contractors, and we still do, and they're absolutely critical to the program because you kind of need a giant aerospace contractor to build like
scale,
a module, right?
Absolutely, yes.
You're probably not going to do that. There's some startups that are working on it. I wish them luck, but it's
going to have a little
it's
difficulty.
tough. But then what you do have, because you have all of these commercial space stations in low Earth orbit, is now it's not government hardware that NASA is setting out a contract, and we're going to own the hardware, and we're going to buy this hardware, and it's ours, and we're going to operate it, which is how we used to do things, and we used to do those all in cost plus contracts. Now we're doing these firm fixed price contracts where we're going to say, here's the money and our requirements. You guys go develop this how you want to, and we're going to buy services from you. Of course, we're going to certify it. We're going to make sure it's safe for humans, but there's a lot of review from NASA. But we're going to buy services. The companies still own the intellectual property. And so they can then go sell those services to a government that wants to send their scientists, or a private company that wants to send their scientists to work on protein crystallization. They can sell their services to somebody that wants to build a small autonomous box that doesn't even have humans. And so that has just really opened the floodgates, and it's allowed these smaller and medium-sized companies to compete in this space. They don't have to build a module.
Yep.
They can build a tiny box that's going to do my favorite thing that I really want to see on space station. I'll put a plug out for. I want everybody working on this. I want automated sample prep. I'd like to go from a sample that you want to sequence and have it extract the DNA and get the library ready and get it ready to go into the. So you could have a company that's out there working on automated sample prep that's going to send a tiny box. They don't have to build a module.
And design a sustainable business model around
absolutely.
that focus,
and once you can do automated sample prep, guess what? All these labs out there in the world would really love to have that as well.
That's amazing. Yeah. Well, now bringing it back full circle to the opening, talking about your work as a microbiologist and, doing some of your work at the Whitehead, but then also being in the field in Congo. Part of what you've described is, again, access. So, access, when we think about oxygen and we think about the U.S. and healthcare and innovation, we are privileged, right? I mean, we're so fortunate to have all that at our disposal, and just like oxygen, we kind of take it for granted. But the reality is, disease is rampant around the world, and whether it's viral or cancer or you name it. But we have a large world, and many of those would-be patients don't have access to those technologies. Any comments around the miniaturization that you found in space and its application to kind of the future of access? So being able to take that Keytruda that we know has great benefit to cancer patients, again, building on some of the work that, we're here in Houston and it's Space Town, but, Jim Allison is upstairs. And so a lot of the work that he did in the Nobel Prize around understanding, the immune system and its ability to fight cancer, like building on all of that, but then making it accessible. What are your thoughts around where the field is moving in that direction? And I guess, do you think it's possible to offer more to more of the world to solve some of those problems through miniaturization? Yeah,
I really do. I think unless there's a forcing function, companies will, it's just easier to build a box that sits on a lab bench that has constant power and cloud internet. And you're not restricted in terms of, you don't want to make it too big, but you're like, I've got a big shipping box that I can build out for dimensions. When all of a sudden you need to have something that fits in the palm of your hand, works off of solar power only and probably intermittent solar power and doesn't have cloud computing, it takes more upfront to design that kind of thing. But once you have that device, the overhead of operating it is much smaller. You're not talking about packing up something in a large shipping box that has lasers that has to be shipped incredibly carefully and has to be serviced by an extremely talented technician and has to have parts that are replaced all the time. You start getting it down to a small package. The other thing in space is like, We don't have technicians up there. We're the technicians. And and if you want to reorder something for a resupply for a part, it's going to take 3 months till the next cargo vehicle. So you design robustness into it. You design a piece of equipment that's designed to be very rugged. It's got to survive launch loads. It's got to survive these temperature extremes. Well, in the Congo, our lab was often on the back of a Land Rover that we were shipping on a raft over the top of a river. You're just not going to take a sequencer that's got a CCD camera and a bunch of lasers through that path.
Yep.
So by making it small and miniaturized and also ruggedized, that makes it cheaper to operate. By shifting things towards microfluidics, instead of like having these large liquid handling systems that require robots, you're definitely making that thing cheaper. As you start to get away from the cold chain, again, it's going to take an upfront cost to not have something in the cold chain.
Back to innovation, though, and engineering.
Yeah.
Right?
If you are forced to do that, because we say, hey, if you want to send your thing to Mars, you have no cold chain, then you're going to design it for that, right? If you're designing for the DoD and they say, hey, there's no way you're keeping this thing cold when you're putting it in a soldier's backpack. But once you have those well-supported large industries developing something like that, well, that piece of equipment is perfect to take to the Congo because I'm never going to have a good cold chain there. Yep. And so it forces you to, you put things on filter paper, you lyophilize, you start to get very stingy about your consumables and you figure out how you can reuse your consumables. You don't just throw away mountains of plastic pipette tips because you don't have the room to ship those.
Sure.
So your mass and your volume constrained. That makes you become very sustainable. You have to recycle everything. So anything that you bring into that system, you have to think about other ways that you might use it. So I think, eventually this is going to drive us in space to some really interesting synthetic biology uses. So for example, all this plastic packaging, like you look in the trash can of any lab and there's so much plastic there. But if you could have your wrappers made out of a polymer that you then break down into a monomer that you then put into the 3D printer on the space station, you're reclaiming those materials.
Sure.
You can think about from a synthetic biology perspective how you even do that with human waste. You shouldn't launch things into space if they're not going to have a life cycle and several different uses. And so my thing that I've been saying is like every gram counts on the way to Mars, and it does. You're so mass limited. But if you have that constraint, and the space industry is going to do that anyway, and maybe the DoD to some extent, boy, is that going to drive innovation. We're going to find it's a pain up front. You would never build a business model on doing this up front unless you have to.
Right.
But all the kinds of things that are going to come out of that, it's pretty exciting.
It is. That's really cool. Well, and you've talked quite a bit too about, the application, in your current role in the Army Reserve, and you talked about modularizing some of these things and always thinking about, the soldier, that's the warfighter that's out front. Can you talk a little bit about your experience there? And thanks for serving our country, first and foremost, but maybe just that element of what you do now and how you're engaged in that regard, and also kind of how you're applying what you've learned, obviously, through your journey in space as well. Yeah,
so I work for the Army Medical Department. I'm a microbiologist for the Army, nothing to do with space. And we're really focused on current and future technologies and how we can integrate that. Everything in the Army Medical Department is set up to save soldiers' lives, to regain their function, to take care of people all the way from preventative medicine to treating a battlefield injury. And so some of the things that we're thinking about is these injuries can happen in really far-flung places. And the current infrastructure right now gets those soldiers into a helicopter or to airplane that transports them back to the hospital. But if you have a really large-scale conflict or you are in a really remote place, that becomes harder and harder. And so we're working a lot on what are the things that we can do, again, to take the hospital out of the hospital and the lab out of the lab. How can we take care of people at the point of injury very far forward? And this is the exact same kind of thinking for space. How do we take care of our astronauts, at the point of injury or disease? Talk about very far forward. Mars is very far forward.
Especially if there's no escape.
Real hard to get there.
2 years out, yes.
Exactly. So these things overlap very well. And so, what are ways that we can, it also lets you get to that injured person quicker. You can treat quicker. But again, you're not constrained by the hospital. It's got to be things that can fit in the backpack that you can bring out there. So we may want to do things like bring lab equipment and lab tests further forward in really small portable equipment that we bring out there, and we're testing that person, right where they're injured or right where they're having an illness. And then we also need to figure out how we can take care of more people simultaneously. So how do you use something like AI or automation to allow a medic to take care of a lot more soldiers in the field instead of bringing those back to the hospital where we've got all of this infrastructure? We're never going to get away from bringing people back to the hospital, but there may be some things that we can treat in the field and have better outcomes because we're treating them sooner and we're not waiting on that transport time.
So, our audience, is broad and diverse, and, there's a lot of aspiring entrepreneurs and scientists that are listening to you. And, if you had, one piece of advice, maybe share a moment around your journey that maybe was the catalyst for continuing to, push forward and take the risks. I mean, you've taken a lot of risks. I mean, and that's a common element of a great entrepreneur, a great creator, a great builder. And so, what advice do you have to listeners that would like to follow in your footsteps?
Yeah, I think we get in our own way a lot. Like, I know I do this. And so something that's helped me along my career is when I come across something that just seems ridiculous, like there's some little voice in my head that's just like, do it anyway. What's the worst that can happen? So I started my own lab at MIT. I didn't do a postdoc. It's a special program for Whitehead fellows. And so you come out of your PhD and you just start your lab as a researcher. And I had a lot of grant ideas, and you get PI status. So you can go apply to NIH for grants right away. And I had these things that I want to do.
Scientist,
and exactly.
An astronaut at the same time.
You just start your own thing. And I was like, this could be a disaster, right? But what's the worst that's going to happen? I can't start a lab. I'm not good at it. Yeah, I was in Boston. I'm like, there's a million labs there. I'll get a postdoc position somewhere. And so it was scary. It seemed really ridiculous. It was taking a big risk. But I wasn't great at it, right? Like I had failures. I had setbacks trying to learn this thing. But you just try it instead of kind of censoring yourself and saying like, oh, that's too risky. That's not going to work out. Same thing with, I applied to be an astronaut, just not really putting a lot of thought into it. But then once I got invited for the interview, again, I was like, this is ridiculous. They're never going to take me, right? That's the voice in my head. Like, no way is NASA going to think I'm qualified to be an astronaut. And I was like, what's the worst that's going to happen? I'm going to get a rejection letter. I thought, well, maybe I'll frame that, and then I've got a great story to tell. So like, why not go do this interview and just put yourself out there? It is really scary, but I think we often stop ourselves from doing the exciting thing before we even get there because we don't want to fail. So having a good network around you of people that'll push you and be like, really, what's the worst that can happen? Like, okay, maybe you fail and you're a little bit embarrassed. Your friends are going to pick you up. They're going to take you out for a nice dinner and tell you that you're great. Like you have people in your life that love you and support you. And not trying and not being willing to fail can just really lead you to be much more constrained.
So what's next for you, and what's most exciting as you look at the horizon in areas that you're spending the most time? I know you said that your third career was a geologist. So is that what's next? Or tell us more about what you're thinking for the next chapter. I mean, you have so many more chapters ahead. Well, we do actually get to learn quite a bit about lunar and Mars geology. So I recently took a field expedition into Arizona to wear some mock-up spacesuit exoskeletons to go do geology with a whole crew of trained geologists. I drove them nuts. I was asking them questions all the time about geology. That's great. I was really excited. But a lot of the stuff that I'm working on at NASA right now is the scientific experiments in low Earth orbit, how we can expand that, really how we can get that into much higher throughput into all of these commercial space stations. And then what do we really need in terms of medical technology on the way to the moon? We want to be able to do research on the moon, and we want to do that on Mars as well. And so we're going to probably have to think about things a little bit differently. Even low Earth orbit still has a supply chain. So you get, the further you get, the more these constraints kind of start locking you down. But all that means is that's the more you get to innovate. And you're forced into this system. There's only one way to do it, with a small payload or a small amount of power. That just opens up what you can innovate, because there's not an easier, if you think about like a river flowing, right? You've got the main branch, and if there's a little
stream that's like forced off to the side. That's it. It's got to go. It's this tiny stream, right? But, over time, that becomes the bigger and bigger stream. And I feel like space exploration is like that right now. We're going to be forced in the next 10, 15 years to innovate in all kinds of ways. And I am so excited to see what technologies spin out of that and how that helps our life on Earth.
That's so awesome. So one closing question. If you had one famous scientist that you could take with you in space, who would that be?
Oh, I feel like Einstein would be a fantastic person to bring to space, mostly because he could help explain all the physics of microgravity. And, I feel like he would have really enjoyed a trip to space.
That's a great answer. Well, Kate, it's so inspiring. It's so fun. I really love, speaking with you, learning more about, your journey. And I know our audience really benefited from hearing about you today.
Well, thank you. It's been wonderful to be here.
Thanks for joining us today. It was another great episode. I hope you enjoyed the conversation with our guest today and were inspired the way I was. Looking forward to reconvening again in 2 weeks. Please visit our website at labratstounicorns.com. We welcome any of your comments, feedback, ideas. If you want me to ask certain questions of guests or you have ideas of people that we should be interviewing.
That is all. Goodbye.